everyone! I am so glad to see you back to the Rasa Masterclass. In the previous episodes, we covered a great deal of theoretical concepts involved into the development of conversational AI assistants with Rasa. From now on, we will focus a lot more on the actual development of our Medicare locator assistant to show you how things are implemented in practice and how they work. So I hope you are ready to roll up your sleeves and do some development work. So this is what we are going to cover in this episode. We will update our NLU and stories data to expand the knowledge of our assistant and improve the NLU and dialogue management models. We will also update our custom actions to enable our assistant to run some backend integrations to complete specific tasks. In addition to this, we will implement the form action and enable our assistant to fail gracefully. So let's get started. At the moment, our assistant is very simple and rather naive. It is capable of understanding simple inputs like greetings, goodbyes, user inputs where they ask for a specific facility or where they provide some specific information, and more. With all this, we enabled our assistant to run a very simple facility search action. We will upgrade the skill and allow our assistant to run some backend integrations to pull some real-world data about different health facilities in the United States and use that information to answer users' questions. So the first thing we have to take care of is the actual database that our assistant will use to pull that data from. For that, we will use a publicly available database from a website called medicare.gov, which provides a variety of open datasets, including information about different health facilities across America. The data can be pulled using an API, where a request URL may look as follows. There are different endpoints for different types of facilities, and they are all specified using a resource ID. So for example, the following ID will pull the data for hospitals, but there are different IDs for home health agency or nursing homes data. We can also narrow the search using the parameters like city name or zip code. This is a perfect dataset for us to use to enable our assistant to provide real-world data about specific facilities. In the previous episodes, we trained a very simple NLU model capable of classifying intents and extracting entities. It worked, but it was very simple and quite prone to mistakes because we used a very small amount of training data to train it. So first of all, let's update our NLU data and add more training examples to each intent in our training data file to improve the performance of the model. We added a bunch of new examples for all of the intents and entities that we had in our training data. Those examples should improve the performance of the intent classification, but there is much more we can do to improve the entity extraction in addition to just adding more examples. So let's talk about that. Let's start with an entity called location. Users can provide this detail by either providing a city name or a zip code. What's special about zip codes is that they follow the same pattern. US zip codes consist of 5 digits. A very easy but effective way to improve the extraction of such entities is allowing our model to use regex features, whether or not the specific pattern was matched, to learn that certain patterns should be associated with specific entities. This can be achieved by defining a regex for an entity extraction and defining the pattern below. This is how regex for extracting zip codes will look like. There is something special about another entity we train our models to extract, facility type. If you remember the example request path we have to use to retrieve the data from the medicare.gov database, the data for a specific facility is pulled using resource codes instead of the actual entity values like hospital, nursing home, etc. Providing the request using words rather than codes is more natural for the users. That's why we will have to do a so-called data normalization to make sure that the extracted values can be used to query the DB. For that, we will define synonyms for specific entity values and make sure that extracted entities are mapped to corresponding resource codes. To define the synonym, we have to update our training data and specify which value specific entities should be mapped to as follows. Here, we define that an entity facility type with a value nursing home should be mapped to this specific resource code. Alternatively, you can define synonyms using the following format, where you define a value which a list of possible entity values should be mapped to. The following synonym will make sure that whenever a facility type entity is extracted with a value hospital or hospitals, those values are mapped to this specific resource code, which can then directly be used to query the database. We will do the same for other entity values and define synonyms for them as well. The last thing we have to do to make sure that Rasa NLU model learns to map the synonyms is to include the component entity synonym mapper into our pipeline configuration. From now on, we will be using the supervised embeddings pipeline, which by default includes the entity synonym mapper component in the configuration. Since we made quite a few changes, we can retrain our NLU model using the command rasa train NLU and see how it performs. After the model is trained, let's load it using the command rasa shell NLU and test it on an input. Let's say I need a hospital. You can see that the model classified this input as an intent search provider, which is correct, but an interesting thing is about the entities. As you can see, an entity hospital was identified, but the actual value that was extracted is a resource ID, which we map this entity to using the synonym. Now let's talk about the dialog management. In the previous episodes, we trained a very simple dialog management model capable of using slots, driving the conversation in a certain way depending on whether or not users provided certain details like location or facility type. Since we have a database now which we would like our assistant to query whenever users ask for a specific health facility, we have to take a closer look how our assistant collects and uses those details. Information like location and facility type are crucial for our assistant to make an API call. That's why we have to ensure that our assistant collects those details before an actual action can be run. This is a perfect use case for Rasa forms, a component which can be used to ensure that an assistant collects certain details before running a specific action. So now let's work on the implementation of forms. Form actions have to be defined in your actions.py file. First, let's import the form action method from the Rasa SDK. Form action is a class, just like any other custom action in Rasa, and follows a pretty similar overall structure. Let's go through this code step by step and understand it better. Form actions generally consist of a few main functions: name, required slots, slot mappings, and submit. A function called name is very simple. It defines the name of the form action. When an action facility form is predicted, Rasa knows that it should run the code defined in this form action class. All form actions must have a method called required slots, which can be used to define which slots must be filled in before an assistant can continue with the dialogue. If some slots are still missing, form policy will continue predicting form action, and an assistant will ask the user to provide those details until all of those slots are filled. In our case, we need 2 slots to be provided for an assistant to be able to query the data: location and facility type. Slot mappings is an optional method of the form action, but it's a very useful one. Some necessary slots can come from very different user inputs, which will naturally have different intents or entity labels. By default, form action will fill in required slots using only the values of the slots with exactly the same names. Slot mappings allow you to define how the values from other intents or entities can be mapped to the specific required slots. In our case, the names of the required slots match the names of the corresponding entities, but we can also specify which intents those values come from. For example, the slot location can be filled using the entity values from intents in form and search provider. Finally, we have to define what happens when all required slots are provided, which is called submit method in a form action. In our case, we want our assistant to run the facility search using the provided details and send the options back to the user. Let's take a look at this function in a bit more detail and understand it better. With tracker get slot method, our assistant will pull the current values of the location and facility type slots and use them to run the custom action find facilities, which we are yet to implement. If no results were found, an assistant will send a message saying that the requested facility could not be found in a certain location. Otherwise, an assistant will send the user top 3 facilities formatted as buttons. The message is sent back to the user using a dispatcher method of Rasa. There are 3 things we need to do to make sure our assistant can use this form. First of all, update our domain and include our form there. Then we have to update model configuration and include form policy in our Dialog Manager model configuration. And last but not least, we have to update our training stories with forms. So let's do that now. Let's go back to the stories.md file. The story with forms may look as follows. Here, facility form means the activation of the form, while the line after that means that the policy is running the form action until all slots are filled. The third line means that the form was filled and an assistant can move on with a conversation. This one story is enough to teach our assistant to handle all the happy paths, the situations where the user provides one detail but not another, and the situations where the user doesn't provide any of the required details in general. Let's add another story which will teach our assistant to respond when the user provides all information with their initial request. There can also be some situations where users ask for multiple recommendations. After an assistant provides some information, the user may ask for additional questions. We can enable our assistant to handle this behavior by adding some stories with more dialogue turns, like the following. With forms, we enabled our assistant to collect some crucial details needed to run the facility search. Now, let's update the facility search custom action to enable our assistant to use those details, run the backend integrations, and return the requested information. Back to our actions.py file. Custom actions with real backend integrations usually consist of quite a few methods, and they will highly depend on what DB or API you are using. Here we have quite a few helper methods, for example, to define the endpoints for our APIs. But the most important part is a function called findHealthcare because it's the body of our custom action. Here is what it does. It retrieves the current slot values for the necessary parameters and uses them to create the full path for the endpoint which our assistant will send a request to retrieve the data. A method requests.get sends a GET request to an API which returns the data in a JSON format. If any results were returned, our assistant will prepare the response depending on what has been asked. If no results were found, an assistant will send a message back to the user suggesting what went wrong. There are quite a few functions which we added to this custom action to make it work smoothly. You can find the code in the repository of the Rasa Masterclass. So at this point, we improved our assistant's NLU model to be better at intent classification and entity extraction tasks. We also implemented form action and a custom action for the facility search with some backend integrations. Another improvement we can do is implementing the fallback to make sure that if our assistant makes a mistake, it handles the situation gracefully. If you remember from the previous episode, there are 2 fallback policies in Rasa: fallback policy and a 2-stage fallback policy. For our medicare locator assistant, we will implement the second one, 2-stage fallback policy. So let's see how it works in practice. To implement the 2-stage fallback policy for our assistant, we will update the config.yaml file and list this policy as one of the components of the policy configuration. We will keep the default values of this policy for now and make changes as we build up our assistant. Since we made so many changes to our assistant, it would be a great time to retrain the models and test how they work with all the new features. To retrain the models, we can use the function called Rasa train. And after the models are trained, we can load our assistant using the functions Rasa run actions and Rasa show. Let's have a quick conversation. As you can see, our assistant is now able to pull real-world data and use that to respond to users' queries. So after all this hard work, our assistant improved quite a lot. We managed to improve the performance of the NLU model. We implemented the form action and quite an advanced custom action with backend integrations and even the fallback. In the next episodes, we will continue expanding on the features and functionalities of our assistant. I really hope that you will implement all of these things that you learned about today in your custom assistants as well. And I'll see you in the next episode of the Rasa Masterclass, where we will continue learning and building up our assistant.